Alrighty, everyone. Well, thanks for joining the Silego GreenFET Load Switch IPS webinar. We're going to break this out into two different webinars. At a later date, you'll get a message for the advanced class, and today we have the basic class where we're going to cover essentially what is a load switch, why do we use them, and then talk a little bit about Silego parts, but not a lot in the first class. In the next class, on part two, on the advanced section, we'll go over in a lot more detail the specifics of load switches for a particular application. This first seminar is going to be more of a general discussion of why load switches are used and what are some of the features to look out for, how to read a load switch data sheet, and whatnot. So without further ado, let's go ahead and get started. Bam. So what are load switches used for? Load switches are actually used for all types of things. One of the big initiatives within the industry is to control off power consumption. So many devices, a lot of people are shocked to learn that when you hit the off button on the device really doesn't go off. It continues to burn power and leak current. And really the only way to turn it completely off is to pull the power plug out of the wall to stop the power flowing. But the big problem with that is the user experience is greatly diminished if you're pulling the power plug out of the wall. For example, the other night I was watching a television show and my set-top box accidentally reset. And when it reset, the boot time for the set-top box was measured in minutes. And that's not a very good user experience if you're in the middle of a movie or something like that and you've got to wait for your set-top box to boot. So the set-top box manufacturers understand this, and they essentially leave a lot of critical components in the box on. The same is true with a host of our devices where when you hit the off button, they're actually burning significant amounts of power. Now, it isn't because designers, don't know what they're doing or can't solve the problem. Solving the problem traditionally has been expensive. It takes quite a bit of time in the race to market. There's issues there. There's also the other user experience of people wanting to use faster processors, have more features in their boxes. These advanced geometry chips also leak power. The other feature is people have an expectation of instant on now. Those boot times are just really bad, so people are moving to SSD drives and all other kinds of things and expect to have memories and operating systems pre-buffered, and so as a result they burn a lot of power there as well. The next type of problem in mobile devices in particular is people want to charge while the device is off, and they expect that the charger charges up their battery while they're sleeping, and that's all plugged into the wall, and when the charger's done they expect that charger to shut down and work appropriately. However, circuitry needs to remain alive to check and see what happened. Does that battery need an additional charge? Have you unplugged from the wall and replugged for it? All of these kinds of things are going on in the background to increase the customer's experience, and so much intelligence is built in to make things look very simple. All those things burn power. And so regulators are very aware of this problem, and so they've passed a whole bunch of regulation over the last decade to try to force box manufacturers essentially to watch out about this hidden power consumption in the industry. And one of the major solutions for solving this problem is the load switch. And so Silego, back in about 2009, started to produce our first generation of what we call our GreenFETs, green obviously being for the environmental element of this, to be able to turn on and off power switches in a very controlled, clean kind of way that makes it very easy on the designers to cut these power islands, these areas of the circuit that are burning power unnecessarily, and provide an unparalleled level of control for the design community. However, shutting things on and off is extremely problematic. It doesn't always go so nicely. Now, compounding that problem is the world went from having a lot of things plugged into the wall to being highly mobile over the last couple of decades, and that the trend is only increasing. More and more things are expected to be battery powered and be mobile right along with you. And this presents a whole another set of problems that is even more complicated. And one of that is power sources are not just the wall power anymore, coming through, you know, a wall board or whatnot, but they come through wireless chargers. There's power obviously in the battery, so that the circuitry needs to take its battery from the battery, the wall power, a wireless charger, any of the other types of power sources that are available today. And switching seamlessly between these power sources is not exactly an easy job. Furthermore, the battery life expectations of the end customer have increased dramatically, so that people wouldn't even consider buying a device that's only going to last an hour or two. They want those batteries to last, you know, in a solid day, sometimes a week, if it's an IoT device, months or even years. The next issue is people expect these systems to be incredibly small. One of the secrets to getting a long battery life for a particular product isn't necessarily to have great designs, but it's to make the printed circuit board small, so that within your given area, you could actually have a larger battery. And indeed, that's what a lot of manufacturers are doing. They're getting the printed circuit boards so small that they have a large battery. In order to get the circuit small, you have to reduce the power circuits. And so Silego makes some of the world's smallest load switches. And I thought I would try to make an attempt to show you just how small these things are. And I don't know if I can even get that here. Sorry, I'm not exactly a hand model here, but let's see if we can show you. It's right there. I've got actually pause there. Check this thing out. See if you can see it. Yeah, I'm trying to see on the screen there. That little thing there on the end of my finger, believe it or not, is a load switch that can run over 2 amps of current through that thing. It's less than 30 milliohms of impedance. 10 years ago, this thing would have been over 100 times the size of what I just showed you, and it would have been probably 500 to 1,000 times bigger in terms of volume. That's the kind of advancements that have gone on in this load switch industry that have been driven by the mobile industry's desire to have longer battery power, have incredible amounts of power delivered in tiny, tiny little spaces, be able to turn that power on and off very cleanly, quickly, and that is what Silego is all about. So we have two fundamental product lines that do a very, very good job of this. One is the GPAK product line, which is are little controllers that can hook up to these IPS or integrated power switches and turn them on and off very, very nicely, can sequence them, do all these kinds of things. And so these two product lines that we have are very synergistic with each other. But today, our focus is primarily on the integrated power switch. So let's talk about these load switches in real systems. You know, it's one thing to talk about everything in isolation and things all work nice on paper. But the truth is, in order to get power reduction, what a lot of people are doing is any time that a particular set of circuits aren't used, and I'll call those power islands, you shut down that circuitry immediately. But turning power on and off creates a lot of problems, and we're going to discuss that today. What we're not going to go into today is we're not going to go into the various schematics and recognizing load switch opportunities and where actual power can be saved in terms of what are the values of resistors and all the kinds of very, very detailed analysis. That will be in our advanced webinar, and so look for the announcement for that in the future. The next issue we're going to talk about is also isolation from interference. Anytime you're taking watts of power and you're turning it on and off within a system, this can create all kinds of interference issues that also need to be resolved. Furthermore, we'll talk about something as simple as a discharge. What do you do about all this power that's hanging around on caps and inductors and things like that when you shut the power off? What becomes of all that power? How do you make sure that that power itself doesn't end up bleeding into other circuits and causing brownouts and resets and a whole bunch of nasty things. The next thing we'll talk about is inrush current. When you turn these power rails on, you need to charge capacitors. Capacitors, by their very nature, have very low impedance, and so you get the big currents come sweeping in when you turn the power on. How do you control that and make sure that you don't crash other parts of your system? So let's take a look at some of the most basic block diagrams. We were talking about the mobile systems earlier that have multiple power sources. So one of the common uses of load switches is to be a power switch between a power supply and a DC to DC converter, a PMIC, other circuitry. It doesn't matter what we're talking about here, but having a switch, a power switch, much like you would have in your home, if you think about it as there's a light switch between your breaker and your actual light, and like your mom would always say, turn the lights off when you leave the room. That saves power. Well, the same thing is true in our designs. You want to save power? Turn your circuit off. Okay, and you may have noticed when you have your lights on and your neighbor decides to do some turn their air compressor on in their garage next door, all of a sudden your lights dim because you've got a bad power system in your neighborhood, and you might have noticed that brownout condition. Well, the same type of thing, if it's not taken care of properly, can happen on your circuit board. You can turn on a big heavy load with a load switch, and all of a sudden the other loads nearby, in my analogy, that would be your home, all of a sudden would brown out. On a circuit, that could be nearby power on. That could be a nearby circuit. It could be an IC that doesn't like to see lower power and unstable power and cause unnecessary resets, and that can cause crashes in the system and really ruin the user experience. So we use load switches. Sometimes load switches, we use a lot of them. Sometimes they come in singles, duals, quads. Sometimes they're integrated in particular chips, and Silego has all of these various options to make it work properly. Now, every system's different. Some companies or some designers would like to see that a power rail is, before you switch over to a new power system, you have a break before make. Others would like to say break before make. Other ones want to see smooth slewing of power from one power source to the next, and they don't want to see any dip or variation within that power. And so once again, using our PAK family and using our IPSs, all of these types of systems can be realized very easily and very simply. Now let's talk about rapid on and off and why accuracy is fairly important here. One of the big misnomers of load switches, oh, we'll just use a PFET, NFET off the shelf. We'll go to DigiKey, pop one of those things in, just shut things down and off. But that's not, while that can work, that's not very competitive. And it's not competitive for a couple of reasons. One is, if you want the optimal in power reduction in your system, you want to be able to turn your power rails off, even, let's go back to our analogy of your room, even if you left your room and your mom told you to turn the lights off, even if you left your room for 30 seconds, you should be able to turn your lights off and on. And the same is true, once again, in our analogy here with a circuit board. The more often you can turn an unneeded circuit on and off very, very rapidly, the more power you're going to save. However, if you've got load switches that aren't very good ones and not properly designed, or have a lot of error in terms of how fast they turn off and how fast they turn on, well, you might have so much error that you really can't even turn them off and on when you don't need that load, because the error budget in how fast you turn on and turn off is so high that you just have to leave it on the entire time. Otherwise, the circuit won't be on when you actually need it. This is kind of a big deal in terms of the types of load switches you'll specify. For example, we'll talk about latency. If the error, for example, in your capacitor is so high that you set up an RC time constant to switch the rail on and off, and that RC time constant has so much error in it, we actually introduce a concept, of latency in the amount of time that a power rail can be brought down. That latency means that you can't turn this power rail on and off when you want to. Therefore, the power rail has to stay on. Therefore, you're burning unnecessary current. So to the extent that you can define how quickly you can shut something down and how evenly you can bring something back up, this will help you to actually be able to turn that switch off more often and save power in your design and make a better, more, you know, ultimately a better user experience, because they're going to see longer battery life. Now, when you do turn something on and off quickly, that introduces a whole set of different types of problems that need to be thought about. And so that's the benefit of Silego's load switches. Here's a common load switch turn on profile. You notice the linear ramp rate here. You notice that you don't see much of an RC time constant here. And part of that is when chip designers specify a chip, a lot of times they specify a particular ramp rate that needs to occur for that chip in order for that chip to come up properly, boot properly, for all the PLLs to stabilize, for all the PORs to operate correctly and reset the chip properly, so that when the power is good, your system is good. And so one of the things we try to achieve more often than not is a very, very nice linear type of ramp that stays, that has a low variance over temperature, and that comes up and is very, very clean. And then you'll notice that when the rail goes down when you go to turn it off, it goes off and it goes all the way down to ground, stays at ground for as long as you need, and it's a very, very clean type of system. Now, that all looks good, but that's not how reality works. If you buy typically just standard P-channel MOSFETs and N-channel MOSFETs, and you hook them up with RCs, and you get all the error associated with the C and whatnot. Sometimes you ramp your power supplies too fast, and sometimes there's too slow. I call it the Goldilocks power on. It's not too fast, not too slow, but it's just right. And so what is just right? There's no answer to just what is right generically. This is why companies have to have a lot of variability in their power sequencing, power turn-on systems, because there is no one right answer. And here's why there's no one right answer. If you look at, for example, a PLL within a chip, very often PLLs are very sensitive type circuits to power ramp. And if they're not ramped precisely where the manufacturer says ramp them, sometimes that PLL may not lock. Sometimes it will cause certain parts of that circuitry to screw up, and you'll have a failed boot cycle. Power on reset circuits are also little nasty circuits if designed incorrectly, and I'll go into exactly just how nasty they can be. A lot of system designers who haven't worked in the industry for a long time are just unaware of really how difficult power on reset circuits can be to design appropriately and to make sure that they're absolutely robust under all conditions. I'll just give you a quick example of how tough it can be. Let's say you go buy a chip from one manufacturer and you buy another chip from another manufacturer, and they both work at 3.3 volts. One manufacturer might have set their POR to kick off at 2.5 volts. Another manufacturer might have done that same 3.3 volt supply part to kick off the POR at 1.8 volts. So as you go to ramp up this 1.8 volt POR in your 3.3 volt chip, all of a sudden triggered, and that chip is up and ready to go. Meanwhile, this other chip that was triggered at 2.5 still hasn't reset, and one chip's trying to talk to the other chip, and one's not ready to go. You've got a problem. So what do you have to do in that case? You may have to speed up the ramp so that by the time the first trigger has happened, the other chip is already in, and therefore you need to supply power even faster. A third chip might have that PLL that I talked about that needs a slow ramp. And so what happens is when you start looking at these systems, you'll find that where you need to ramp your system has a particular area that works better than others. And indeed, it may turn out that there is no right answer. Maybe there is no Goldilocks zone, and you end up having to have two load switches, and you have to sequence them, and you've got to power up these three things, hold off a circuit that's already active, and then power that up subsequently. So power sequencing benefits enormously from configurability to be able to do things at the last minute such that your system is reliable. And then, of course, like all system designers, you have to guarantee it over voltages. You can't guarantee that your power supply is exactly dead nuts on. It's got to be plus or minus 10%, or maybe it's a battery powered supply and it's variant, so you got to guarantee it over that. Then you got to guarantee it over temperature. Then you got to hope that your semiconductor manufacturer shipped you parts that are representative of the process that they're ultimately going to send you. So, bottom line is, if you're going to do IPSs right, you want to have load switches that can configure their ramp rates. You want to have load switches that can have various options on your discharge, and then you also want to control them with systems that are highly configurable. Now, let's talk about ramp rate variation. Our first generation of products we called the GFET 1. These offered, in many cases, closed loop control for high voltage MOSFETs. And the whole point of that was to get the load of the system to be somewhat independent of the turn-on ramp time of a particular chip. So a lot of times in big companies, for example, you'll have the power supply designer is independent of the system designer. And as a result, the power supply designer may indeed design a particular power supply to ramp at a particular rate and for a particular load. But if that load changes, that rate can change. So one of the points of the GFET family, and we'll go into this in the advanced seminar in a lot more detail, was to make the ramp rate somewhat load independent. So these are closed loop designs so that MOSFET is turning on at a very continuous rate that varies very little over temperature without respect to what the load is. That ramp rate in those early GFETs was dictated by simply a current source feeding onto a semiconductor capacitor, which is very different than a ceramic capacitor, which can have quite a bit of variation. Now, on a lot of the load switches, including a lot that Silego sells, their ramp rate is set by a capacitor. And once again, there's a lot of ways to do that, but very often there's a little current that flows onto the capacitor, charges the capacitor up, and that becomes the gate voltage for turning on the MOSFET. Sometimes a pump will do that. Other things. I mean, we sell more than 200 different types of load switches, so there's a lot of different ways we do this depending on what the application calls for. But nonetheless, you have to be aware that a capacitor value that you buy off of a catalog distributor is not indeed the number that you actually get when you put it into the system. Yes, that's what they tested at, and nobody's being fraudulent here, but the value of the capacitor is dictated by the temperature. Temperature can vary. The capacitor values, even ceramics, can vary by more than 50% over temperature unless you're buying an MPO style. You also have to understand what the working voltage is. If you charge a capacitor up to 10 volts, it's going to have a different level of capacitance than that same capacitor has at 5 volts or 3 volts. Furthermore, you get process variation. A lot of companies, you get a cheap capacitor, it'll be plus or minus 20%. That's what they're guaranteed. So you have to be careful to understand the nature of your capacitor. And this webinar here is not going to go into every detail of capacitors or how they work. That, although it is an incredibly fascinating subject, but suffice to say, one of the biggest errors that you're going to have with respect to load switches and ramp rates is in what type of capacitor do you choose. Other types of our load switches use resistors for control, and they'll have a setting resistor, and that resistor, resistors are beautiful little devices for given how cheap they are. They're virtually free, and they're plus or minus 1%. They've got great over temperature performance, and so one of the biggest error sources left when we use our resistive style of ramp rates is the error associated with the currents and other ways that we bias that resistor to set up what the ramp rate is to be. But most of the error in that case is not coming from the resistor itself. And then finally, we have a couple of programmable options where you can go in with NVM and set what the ramp rates are. Now, let's talk about discharge. Turning these things off. It seems really, really basic that, well, you just shut things down, but what is down? So there's a couple of things for starters. Is within load switches, especially these little tiny, tiny load switches I was showing you earlier, you can't put 10 ohms and expect to discharge 100 microfarads within a microsecond through a load switch, because that's an incredible amount of wattage. You would heat the device up, probably melt the solder and that kind of thing. So we limit a lot of our discharge resistors that are integrated into these chips to 300 ohms, 1K ohm, 2K ohms, these types of numbers to prevent any kind of reliability issue within the chips. If you need 10 ohms of external discharge to really get a power rail shut down all the way to ground really, really quickly, you'd probably want to use an external discharge at that point. However, in many mobile applications, especially ones that are load switching between two power sources, there's no desire at all to discharge the rail, and in which case we offer piles and piles of load switches that have no discharge whatsoever associated with them for those types of applications. Now, what happens when you turn something off? What if you go to turn a rail off, but it doesn't really discharge, or maybe it doesn't discharge fast enough? You're actually creating a brownout system. How do you know that the downstream chips have even recognized that as a power off, that the power actually turned off? Maybe some of those chips were designed on slightly more advanced geometries than the one that your load switch is designed on, and so they're quite happy to work at a reduced voltage, and they'll continue on rocking. And let's say you turn the switch back on even before that rail has been discharged, and indeed you don't know if your downstream chip is actually working or not, or whether it reset or not, and so that can be a very problematic kind of thing. The other thing is you may have indeed triggered the reset, and that chip indeed reset. Now, it gets really messy. What is off? I think all of us agree that if you take a power rail and you take it within a few microvolts of ground and you leave it there for 10 seconds, a minute, that is off. And I think the average consumer sometimes sees this, that once again, when you talk to set-top box manufacturer or something like that, or any of the consumer electronic manufacturers, they'll tell you to pull the plug out of the wall and then wait 3 or 4 minutes before you plug it in to make sure it properly reset. The reason why they're saying this is because all of the caps in the systems, and to a lesser extent inductors or other kinds of things, are holding charge, and that charge needs to dissipate. And when the loads are off, then maybe that charge isn't dissipating as fast as you might think. And what happens is a lot of the power on resets that exist within all of the SoCs and processors and microcontrollers throughout the system, their PORs all have different trigger levels at which they detect that the power is no longer good, and so that the next time power comes up to make sure they properly reset. In the meantime, their latches and their memory banks and stuff like that may have been corrupted, so that if you just powered on before they properly reset, once again your system would crash. Now, to make the problem even more sadistic, many times in the power on reset circuit, there's actually areas where the reset circuit works, and there's areas, voltages, at which the reset circuit doesn't work. For example, if you go down all the way to ground, I think most of us would agree that most power on reset circuits would work. However, what if you didn't stay at ground long enough? I've known POR circuits, power on reset circuits, that don't work properly unless the power is off for a period of time. And the reason why is they have floating nodes within those circuits that once you're down below a diode drop off the negative rail, those floating nodes don't properly reset. So if you don't give time for the charge to bleed away in those, and then you just turn your chip on again, your power on reset circuit doesn't reset properly, and you get a bad, and your chip doesn't reset at all, and you get a bad crashing result. I've seen POR circuits that worked fine for the first 300 millivolts off of ground, but somewhere between 300 millivolts and 500 millivolts. If the charge had only bled down that far, between that and the time you powered it back on, the system crashes. And so there can actually be holes where the system will crash at particular voltages and be perfectly acceptable at 50 millivolts higher than that. So once again, this illustrates the need for a configurable power on sequencing type of system that is made possible by the Silego GPAKs and IPS switches. And you can't just assume that semiconductor manufacturers are going to put all this type of data in their data sheets. In fact, I've never seen this type of data in data sheets. And it's one of those things, and until you experience it, you might not appreciate just how important it is. Here's an example of incomplete discharge. And one of the reasons you get incomplete discharge is because semiconductor circuits basically shut off once you get down to their voltage threshold, and it's extremely difficult for manufacturers to build in circuits that are going to completely discharge all the way down to zero when there's absolutely nothing left alive in the chip to do that discharge or to turn that switch on. And so you actually can have charge trapped on capacitors that, you know, could take a matter of minutes to bleed away. Here's an example of complete discharge where it's brought all the way down within a few millivolts of the rail, and that can often result in a much cleaner power on loop. Now, one second here. Once again, if anybody has any questions or that type of thing, feel free to ask. A lot of times questions result in a much better dialogue going on here. If you're able to do that with your, or pass along with a message with chat, I'm able to see those things as I'm giving a seminar here. Now let's talk, let's continue on and talk about the load switches in multiple load island or power islands, if you were. When you look at an entire system today, what you'll notice is that there are functional blocks within a particular design. That functional block may be, let's say, a video. Maybe one of these load panels is load islands rather, is a video screen, and associated with the video screen is going to be circuits to control the brightness, dimming, you know, level shifters, because the chips used in the display screen are more advanced than the microcontroller maybe that's meant to drive it or communicate with it. And as a result, you get a island of circuitry associated with that video screen. Maybe another load island or power island is associated with sensors. You're going to do accelerometers, and you want those particular power rails to be very clean. So you've got more regulators out there and whatnot. Maybe some of those are microphones. Maybe some of those are temperature sensors. Who knows? But the point is, there's power associated with a particular set of circuits. And when you don't need those circuits, you want to switch them off. And even more than that, especially like on sensors, you get a thermistor, it might be a 100K ohm type of device. You don't want to have that permanently biased. You want to be able to switch that off when it's not going to be used, because you're going to have a lot of current flowing into that otherwise. A number of these things, especially like on the video panels I was bringing out, generally leak. These are huge devices. They use a lot of silicon. It's very advanced silicon. And as a result, they leak like a sieve. And so you can actually have tens, if not hundreds of microamps continuously flowing into these circuits. And if you don't shut them all the way off, you're going to see a substantial reduction in your battery life. In wearables, for example, I spent the last couple of weeks doing a lot of analysis on wearables. And it turns out that if wearable devices are turned off many cases, 99% of the time, 98% of the time, and are only alive 2% of the time. Now, what 2% of the time are they alive? Well, a lot of times they're pinging a Bluetooth, and maybe they're waking up once a second, sometimes once every 2 seconds, and the rest of the time they're completely asleep. So there's a big trade-off in those cases between, for battery life, or how many picojoules or nanojoules are you using, between the leakage current and the load switch RDS on. That will be for our advanced seminar to talk more about that. But nonetheless, it all speaks to the importance of leakage current. So we put in the load switches to handle the leakage current and cut that. But the problem is you have these capacitors sitting there. The capacitors are often needed for proper decoupling because the power supplies may not have fast enough response, and therefore we decouple these panels, our sensors, other ICs, microcontrollers, and when those capacitors are fully discharged, they're just sitting there waiting for current. And when you turn on the load switch, you're going to get a big inrush current flowing into that capacitor, because most capacitors have ESRs, especially ceramics, you know, that are down in the hundreds of milliohms, tens of milliohms, and so you could drive a lot of current into these capacitors really, really quickly, and you need those capacitors to charge up relatively quickly in order to be able to have fast response time on your loads for turn on, turn off applications. The problem is exactly what I illustrate here, where you've got a resistor here in your power rail. It's not an actual resistor, but it's the natural IR drop in how you lay out your power circuits. It's one of the reasons why everybody encourages designers to put in power planes, is to eliminate or actually mitigate the amount of resistance they have in a power plane. But you could imagine if you have current flowing rapidly into a capacitor, where's that current going to come from? Well, if you have a load switch that's on already, that current may indeed come from another capacitor. It might not come from the actual power supply, in which case you could get a brownout condition occurring in a nearby power island. This graph, or this actual scope photo, kind of shows you what happens here. We're turning on a power supply pretty quickly. I mean, not outrageously quickly, but in a few hundred microseconds it's coming on. And you'll notice that the amount of current flowing onto the cap actually puts a little bit of a dip into the drain side of the load, or essentially the part that's going to ultimately connect to the power supply. It puts a little dip in there. You could imagine that if I turned it on a lot faster, that dip would be a lot sharper, it'd be shorter, and if that dip got large enough, you could actually cause a problem in nearby circuits and cause unnecessary power on resets. So this brings us to the subject of inrush currents. The amount of inrush current that a particular capacitor can cause in a system is actually quite remarkable. If you're using, you know, 100 microfarad cap, it wouldn't be uncommon to see currents as, you know, well up into the amp, you know, tens of amps range, depending on how fast you turn on. You could easily experience 10 to 15 watt types of numbers within a load switch of power that needs to be dissipated, even with a fairly low power load switch. So the way we control these types of sudden surges of current and ultimately power and things like that that are going onto these big capacitors is we've got to slow down the turn on of the load switch. And by controlling the ramp time of that load switch, we can actually control the inrush current. And the two indeed are directly proportional. So the slower the load switch comes on, the more the less inrush current you have. But obviously there's a trade-off here. If you go too slow, that could be a user experience problem. It can slow your system down when you want to actually do things that are meaningful. And so Silego offers a whole host of different load switches that allow for, you know, a little bit of control of the inrush current to a lot of control, to fast, and all different types control. It's really remarkable, the numbers of switches and the ways that we do this. So once again, that will be in the advanced seminar. But suffice it to say, anytime that you have a larger cap, Silego is a good company to call to figure out what type of ramp rates that you want. And our FAEs are well trained up in helping select the right types of load switches for these types of applications. Now, up till now, I've been using these really basic blocks. So let's take a look at an actual type of system. Once again, it's still sort of idealized, but I kind of want to show you the complexity that's involved in common systems. And this was from an actual reference design from a company that'll go unnamed. It is a public reference design, so there's no problem with that. But here's the type of system that you'll see. So wall power over here, it goes through a fuse. Often there's an RC type filter in case there's any kind of nasty stuff going on in the power line. There's companies that make power line communication, and we don't want that type of spikes flowing into it. You might have lightning strikes and things like that on the line. We want to make sure those are filtered out. And so a lot of times there's a power supply filter that's going on here that's once again limiting the things. Then you want an overcurrent protection for your circuit because safety matters. You don't want situations like happened to the big consumer company where they're starting to have fires and that kind of thing as a result of how you plug in. So there's an overcurrent protection switch that goes in there. That adds a little bit more impedance on the power line. And once again, because that impedance is there, you need another capacitor to kind of buffer that to get your response times back up. Then you have DC to DC converters to knock down the voltages to something that's useful for most advanced advanced semiconductors. There's inductors that are associated with the DC to DC converter, and then finally you get to the lower voltage load switches. And sometimes the load switches are in parallel because in a hibernate mode, maybe the first power rails pick off for that, and then you get an all active mode and you have another load switch for that. There's a whole bunch of different reasons why architectures are the way they are. But this kind of gives you an example of just how complicated a system can be, not to go into every detail of the system, but to show you that Silego products find their way into very complicated systems. Most complicated systems can be somewhat idealized, and we can pick out what is the right ramp rate for your load switch, what's the right value for your load switch, what load switches run at particular voltages, and also meet the various sizes requirements for the customers. But that, what I show here, is what real systems start to look like. Now, when you open up very common reference designs or large SoCs that are available from image manufacturers or large FPGA manufacturers or large processor manufacturers, these types of companies often have multiple PLLs within the same exact chip, and they have multiple power sequencing requirements even on the exact same chip. Now you can imagine you use 3 or 4 of these chips in a system, and each one of these chips has multiple power rails with multiple sequencing requirements, and they want to guarantee that this rail comes up before that rail, also that their PORs will all do the right kinds of things. It gets really complicated really fast, and the point of this slide isn't to go, oh, check this out, is there anything meaningful, but it's to show you just how precisely spec'd these particular power rails are. And what's awesome about the Silego solutions in terms of the GPAKs and the IPSs is you could throw a 16 power rail spec at a Silego FAE, and literally within 48 hours, that FAE could come back and say, here's how you control that entire system. I can meet all of your timing. I can meet all of your ramp rates. I can meet all of your discharge rates and give you an entire power tree for everything from 20-volt parts down to our 5-volt, 3.3 volts, and give you incredible performance in a small size, no matter how complex it is. And the complexity doesn't, once again, start with the off sequencing. It goes to the on sequencing. It also extends to the off sequencing. The off, how you turn a device, these large devices off, is just as complicated as how you turn them on. And so once again, all of this can be immediately handled with the types of devices. So this takes us to the next section of our seminar of what's in a load switch. So I wanted to walk you guys through all the fundamentals of a load switch. What constitutes a load switch? Why do we make the trade-offs? And this will ultimately help us to read the load switch data sheet much better and start to understand what the trade-offs are for our customers. So let's talk fundamentally. Well, there's two fundamental types of load switches. There's ones that use N-channel MOSFETs, and there's ones that use P-channel MOSFETs. They get a lot more complicated than that. Just bear with me here, especially for those of you that may know this kind of thing. N-channel MOSFETs are generally higher performance than P-channel MOSFETs. Not always, there's lots of caveats, but generally speaking. And the reason why is N-channel MOSFETs use electrons as their primary carrier, and P-channels use holes, or the lack of electrons, as their primary carrier. Well, electrons flow through silicon 2.2 times better, their mobility, how fast they zip through there. So N-channels have lower resistance than P-channels, all things being equal for the same exact size. That's a good thing for N-channels, and it's why the vast majority of the load switches that Silego ships today are N-channel load switches. Now, there's still a lot of use for P-channels. They're amazing devices unto themselves because you can sometimes get lower power load switches by using P-channels. None of that changes, but tablets and these types of things that are running a couple amps of power around generally can afford the N-channel MOSFET, because N-channel MOSFETs also have some nasties associated with them, even though they're more friendly, and we'll talk about that in a moment. So we start with the N-channel. So the question is, how do you turn it on? Well, in order to turn an N-channel MOSFET on in a load switch application, the load switch is often the drain and the source are at the VDD of the chip, so to speak. We're not going to run another VDD over to our load switch. We're just going to use the voltage that's already available there. So in order to turn the N-channel on, we've got to drive the gate above the voltage of the drain and the source. That means we have to have a charge pump. That charge pump burns power. So we're not going to load switch a 10 microamp power line with a charge pump that's 10 microamps. That's why normally when you're putting a load switch in, you're talking about things that are burning, you know, at least 50 milliamps, maybe as low as 10 milliamps. But if you're going to use an N channel, that charge pump's going to be going. That charge pump can, you know, be on the low side of a couple of microamps, and, you know, typically 10, 20, 30 microamps for a larger load switch that can switch, you know, 4 amp, 5 amp, 6 amp type currents. The bigger the gate is, often the bigger the charge pump that needs to turn it on is, in order to turn that MOSFET on at a reasonable rate of speed. Now get this, when the N channel is off, we want to take that charge pump and also turn it off. That means, though, that when we go to turn the N channel on, we're turning that charge pump on. It's not just sitting there having pre-charged a cap up to a particular level and then we switched it. So that means the charge pump needs to be bigger, the bigger the MOSFET is, or the more current that you want to switch. The N channels are beautiful in this sense. I mean, the P channels are beautiful in this sense, that the gate, in order to turn it off, just has to go up to the drain and source, and to turn it on, we just drop it, you know, down on the ground, and you've got it. So at any rate, so Silego makes some incredible MOSFETs. In the beginning part of our advanced seminar, we'll talk about the process. We'll talk about the revolution that's happened in the MOSFET business over the last 5 years that have allowed the dramatic size reduction in load switches that is just absolutely remarkable. And I mean, like I was saying, it's almost mind-blowing to think you can put, you know, 2 amps through something that's a half a square millimeter of silicon, and add safety circuits and all the other kinds of things that go on like that. I would add, though, in an advanced seminar, and one of the reasons you probably want to be in that is we will talk about the safety circuits. along with this massive size reduction, there's been a huge increase in the energy density going through these little tiny devices, because you can imagine if you're up at 3 volts and you're putting 2 amps in here, and there's a short in this little thing, and all of a sudden this little tiny thing that looks like a pepper speck all of a sudden has 6 watts running through it. Quite remarkable things can happen, and we're going to show you that in the advanced seminar. But to suffice it to say, Silego parts are extremely safe and extremely robust, and some of our competitor parts look like a Marlboro commercial. So we'll talk about that later. But so the way the typical N-channel MOSFET works here is we often internally bias or have that charge pump up to 5 volts above the drain and the source for our N-channel MOSFETs. And that results in a pretty good RDS on. You can see that you start to get diminishing returns after 5 volts. And 5 volts is just a really nice place to go put that for our particular process, and you get a low RDS on. Now, one of the nice things about that is we actually, if you'll notice the comment down here, we actually regulate at that 5 volts. So we keep it there. If you homebrew your load switch with using a discrete MOSFET and using some other transistors and resistors and caps and that kind of thing, most of the time homebrewed circuits are not going to actually regulate the bias that goes on the gate. So as the power supply changes on the drain, the actual impedance of the load switch will change as well and becomes another air source in your system. A lot of designers love the fact that when they turn a Silego load switch on, and our data sheet says you're going to get 7 milliohms or you're going to get 30 milliohms, whatever the load switch is, that's what you get. And you get that without respect to what your battery's at. If your battery decayed from 4.2 to 3.3, you'll still get the same milliohms because we're regulating that 5 volts above the drain no matter what the input source is. And that once again, it's a really nice elimination of a significant error source, so you don't have to worry that you're getting your impedance of your load switch is starting to become a meaningful part of your system power consumption budget when the VGS value starts to drop. So the next thing we have to consider, a lot of people are, system designers are unaware that in many load switches, we have the body diode effect, just like when you buy a regular MOSFET, that if you have a higher voltage on the source in your load switch, you can indeed have current flow back through the device into the source, into where the power is coming from, the drain. Remember in our old school, we called drains is where the power comes from, and sources is where it's going to, and it's all backwards, so just remember that. Your body diode can be pointed in the wrong direction. In most N-channel single MOSFET types of devices, that's something you need to concern yourself with. Now, there's a lot of solutions to that. So one of the most obvious solutions, we can add another MOSFET that's pointed in the exact opposite direction and turn both of them on, and we call this reverse blocking. And this is important when you're using multiple power sources, because just because you charge the battery, that battery still's got power on it. So when you pull the charger away, you don't want that battery power to start flowing the opposite direction and go and start to rebias your charger circuitry. You want to make sure that's all cut off. And so in many cases, you'll use a reverse blocking type load switch, which is simply 2 load switches. There's other techniques that we use to cut down the size. You can have bulk switching techniques, and there's a whole bunch of other things that we're not going to get into in this particular part of the seminar. But in a very basic sense, you can add another MOSFET, you get reverse blocking. Very important for super cap applications, battery applications, charge bank applications where you want to store power. Now, the next thing we know is we've added our charge pump, we've got our MOSFET. We have to have some ramp control, and there's a whole bunch of different ways that we do the ramp control. We talked about earlier, resistors, capacitors, programmability, but essentially that ramp control, because we want that charge pump to turn off when the device is off so we don't burn any power other than the leakage of the quiescent current of the device. That ramp control needs to come on when you turn it on, controls the charge pump to come up in a particular manner, whether you want it up fast or slow. And we've got to provide that flexibility in the system so we can get you in the Goldilocks zone that we were talking about earlier. Now, we have to have a discharge resistor, and indeed, that's what we put on it. That discharge resistor needs to be low enough to discharge the load appropriately, but it has to be high enough not to cause a problem internally in our load switches by dumping vast amounts of energy in there and heating up these little tiny load switches. Now, that concludes our seminar. Is there any question? First part of our seminar, we'll get into the process, we'll get into safety circuits, we'll get into specific types of load switches in our advanced seminar. Are there any questions from any of the viewers online? Okay, I don't see any questions from everybody, so we'll go ahead and conclude. It would be really great. Oh, somebody asked, what are the typical input leakage currents when the load switch is off? That's a great question, and it's highly dependent on a lot of different things. But I would say, if I just generically speaking, they're in the tens of nanoamps is a pretty normal type of spec. A lot of times we'll say in our data sheets it's just less than a microamp, and what that generally means is that's what we tested it on our test system, but the reality is it's much lower than that. In other cases where the drain voltage is down a long ways and there's not much VGS available, let's say in some of our P-channel options, you'll see the leakage currents will kick up a little bit in those cases. And so it really is on a load switch by load switch basis. But if you just get your generic, hey, I need a 5-volt rail switched and I got 2 amps on it and I'm going to buy a normal N-channel load switch, the answer is you're down in your tens, less than 100 nanoamp kind of range. Hope that answers your question. Does anybody else have a question? Okay, well, thank you so much for your time, and I hope you found that useful. Yeah. All right, Paul. I'd go ahead and give out my email because I don't know who online where your FAEs are, but we do have load switches for very long battery life applications that can even get it, way down. So my email, and I'll probably end up forwarding you off to one of our FAEs who do a great job, is jmcdonald@silego.com. You can forward me that email and I'll pop that out to the appropriate FAE, and I'd love to work with you one-on-one and make sure that we get you exactly what you need. Alrighty, thank you so much, everybody. Look forward to the announcement for the advanced stuff, and we'll go into safety circuits and new load switches and all that kind of good thing. All right, you take care. Bye.